Dr. Phys, Theoretical Physics. Before we proceed with looking at the Schrödinger equation, let's consider some wave properties in general. Here I have a wave that's moving to the right, a sine wave. And remember, you cannot put into the sine function something like meters. You have to have a dimensionless quantity. Like radians, for example. The sine of pi would be a value. Pi is independent of feet, meters, because of the radian definition where you take a ratio. So here I have k inserted in front of my x minus vt form, which gives me a wave moving to the right. And I want to understand, what is that k? What is the meaning of that k? So this is our wave moving to the right, and I put the k in there because I want to use a sine, a very, very simple function, to look at my wave. So here is the sine function, sine of u, where you have the u argument in radians. So, sine of pi over 2 is 1, sine of pi is 0. And how can I relate that to k? Well, let's see. What we do is we take a snapshot. We say at t equals 0, take a picture. Freeze the wave. It's a photograph. So at t is equal to 0, I have sine of kx. There it is, sine of kx. Now, if that's the case, watch what happens if I look here along the u-axis. If I look here, one whole cycle. One whole cycle, that is defined as the wavelength in space. So k times the wavelength in space must map to 2 pi in my sine function. So that's the key idea. The key idea here that k times lambda is equal to 2 pi, and then k is 2 pi over lambda, is sometimes called the wave number, since if you kind of divide the wavelength into 2 pi, it tells you how many wavelengths there are, right? The wave number. So that is the nice formula. And if we go to looking at the angular velocity, that is something that comes out of here very, very naturally. Let's see if we can understand this. If we look at here, freezing yourself in space, in other words, we stand at x equals 0 and watch the wave go by, sort of a nice argument. It's kind of like this is the time sort of analysis. The other was a space analysis. And for the space analysis, we took a snapshot, t equals 0, and here for the time analysis, we settled down at x equals 0 and just watch the wave wiggle as it, as it goes past us. So when we look at that, by waiting, say, the period, capital T, if I wait the period, then my kv here, if I wait the period, capital T, that corresponds to one cycle in time, then kv, capital T, must be 2 pi. The time analysis version of what we did earlier at the space analysis. When you do that, you see kv is 2 pi over t, and that brings us to 2 pi frequency is equal to what's called, the angular frequency, 2 pi f.